Presently, he is an associate professor in the Department of Mathematics at IIT Ropar. Dr. Raju's areas of research interests include matrix analysis, geometric aspects of function analysis, approximation theory, fixed point theory, and applications. And it gives me once again pleasure and privilege to read the profile of the Raju sir. Over to you, Raju sir.
Thank you very much for the introduction. So, good morning, one and all. I hope you had nice welcome for this conference. And this conference is in data sciences and artificial intelligence. Am I right?
Yes, sir.
Yes. Okay, but I am a mathematician. I don't know how you can digest my talk. I will be since you are all not very familiar with all classical proofs and theorems of mathematics, so I will ignore all the proofs. I will try to give my elementary talk as less details of mathematics, and I prefer interaction than teaching, though it is a keynote talk. If anyone have any doubt or any clarification in between, I request one and all, every one of this section to raise your hand or make a comment, so that I will pass some time for my talk and I will clarify these discussions. Hope I am clear.
Yes, sir.
Yes. Is my screen is visible?
Yes, sir. It is visible.
Yes, please. For yes, I am getting some messages. Once again, good morning. I would like to discuss on diagonalization of matrices along with SVD, PCA with applications. So the motivation of my talk is as a mathematician, how we can think of matrices will be useful for either data sciences or image analysis or somewhere. So with this, I will start my talk. The outline of my talks, like the outline of topics are the following. First, I will give some very brief introduction to linear algebra, which is a framework which we need for this session, and diagonalization of matrices. Then we will go to SVD and some applications of SVD, then PCA, and another one more application. If time permits, we will see some more applications. What is vector space? Vector space is nothing but a space. That means that we have vectors. We have a set. For example, let us see that V denotes one set for us, and which is a non-empty set. The elements we are usually calling as vectors. Let us see why we call it as vectors little later. And then on this vector we have an internal operation addition. That means that if we take two vectors, addition of two vectors be also a vector that belongs to V, and we will have null vector in this space. That means that a vector 0, that says that if I add 0 to any vector, that does not reflects or does not react anything on our vector. Similarly, we will have a external operation which is called scalar multiplication, which says that every vector V we can multiply with a scalar real number, let us say alpha, then alpha times x is a vector, or alpha times V is a vector in that space, and we will have a unit vector 1. And one of the important notions I would like to use is linear dependent of vectors. What is meaning of linear dependent? For example, let me give one example. Let us see, in a family, our kids are studying. Our kids are studying means we are sponsoring some money to them. That means our kids are dependent of ours. That sequence is saying that whatever they spend are coming from either father's income or mother's income or somebody income. Similarly, two vectors are said to be linearly dependent if one is completely depend on other. That means that one vector is alpha times another vector b. Similarly, three vectors said to be linearly dependent. One of them must be depend upon either one or other two. That sequentially saying that I will write for the time sake. Hope my slides are clear. Suppose three vectors v1, v2, v3 are linearly dependent. These three v3 or any one of them will be depend upon either this vector or both. That means whatever v3 spends, this is, let us say, this is the amount spent by v3 will be given by a partial from father, if another partial amount from the mother. That sequentially we can write it as alpha times v1 plus beta times v2 plus minus v3 is equals to 0, where these partial amounts are non-zero. That means that three vectors r n vector is said to be linearly dependent if we can have such a equation, like if I have v1, v2, vn are linearly dependent, if we have such kind of equation with one of the scalar is non-zero, this either v1 or v2 or alpha 1, alpha 2, alpha n, among that at least one of them is non-zero. What does it mean that linearly independent? Such kind of thing does not happen. That means that father and son both are earning equivalently. They are spending their own money. They are not depending others. That means that this vector, father vector and son vector, they are linearly independent. That means nobody is taking money from other side. That means that if we have written this type of equation, in this, these two are zeros. Why am we are saying that these two are zeros? If one of them is non-zero, let us say this is non-zero. If this is non-zero, we can take this element to right hand side. Then what we will get? Alpha 2 v2, which is equals to alpha 1 v1. And since it is not 0, I can divide that element from both the side. That means here I will get 1, here I will get alpha 2. That says that the sun vector is this many portion, the amount of sun which he is spending is taking this many part from his father. That says that it is linearly dependent. So if we want linearly independent, such kind of thing cannot happen. That means that alpha 2 cannot be 0 as well as alpha 2 cannot be non-zero as well as alpha 1 cannot be non-zero. That says that in this equation we will have both of them are non-zero. Similarly for n, maximum linear independent set is how many we can get maximum. For example, in a family, how many can n? Total number of family, how many are there? That many can n. More than that, they can. Suppose I have 5 members in my family. Can I take 6 members which are linearly independent? It is not possible. So in a vector space, only maximum linear independent set is, let us see what could be this. That maximum linear independent set, we can say it is basis. Otherwise, a set is said to be basis if every element of every vector can be written as linear combinations of like this basis vectors. So dimension, number of elements of the basis is called dimension. Inner product space, what is inner product space means? In a vector space, can we have angle between two vectors? If such a thing is happens, then we say that space is inner product space. Similarly, angle we can define what is the angle is if this is inner product. Inner product is this one. If x and y is vectors, inner product, if we define this one, angle between xy is equals to cos theta. The angle theta is satisfying this property. If y is length of x, norm x is length of x, norm y is length of y, inner product is xy, then this cos theta will satisfy this property. And orthonormal vectors are two vectors which are perpendicular. Angle is 90 degrees. That means that inner product is 0. This is 0. Orthonormal vectors, we can have set of all orthonormal set. That means that we will have a set for which any two are orthogonal. And orthonormal basis, an orthonormal set which all are unit vectors and basis is called orthonormal basis. These are the basic topics I need. So with this we will start. What is our first question? First question is, suppose if we have a linear independent set, can we extend it as a basis? Yes, we can put some more element to make a basis. Answer is yes for this. And second question is, suppose if we have linearly independent set, which is maximal in a inner products case, can it demands or can it generates orthonormal basis? Why it is so? This is important. Suppose if we have a orthonormal basis v1, v2, vn, since it is a basis, every vector x can be written as linear combination of these vectors. So by the way, what is the linear combination? Linear combination means such kind of summation. But what is this alpha n? Alpha 1, alpha 2, alpha n. Can we find it out? Answer is yes, if my basis is orthonormal basis. If my basis is orthonormal basis, alpha 1 is exactly inner product of x times the first vector, basis vector. Alpha 2 is inner product of x with the second basis vector. So that means that if I have a orthonormal basis, then every vector can be written very easily. That means that x can be written as inner product of x v1 v1 plus x v2 v2 and all. That means that the scalars can be found easily. That is the benefit of having orthonormal basis. Now question is that every linearly independent set, can we make it as a orthonormal basis? Answer is yes. And this process is called Gram-Smith process, and it is given by the following method. I'm not really going to describe more because this method is I'm giving to calculate. You can try it so that we will use it in future. Now, what is linear transformation? Linear transformation is, suppose we have two vector spaces. Let us say this is two-dimensional space. Let us say this is one plane, xy plane. This is our three-dimensional space. A linear transformation is just transforming every two-dimensional vector to the three-dimensional, some three-dimensional vector. T is a mission for us. This mission is sending a vector from this space to this space, which satisfies linear properties. What are linear properties? If I take two vectors in this space and if I add them, if I transfer, that should be equals to first transforming each vector and then adding. Linearly it will transfer. Such a transformation is called linear transformation. Suppose this is one of the example which transfer three-dimensional vector to a two-dimensional vector. Similarly, every dimensional vector to another dimensional we can transfer. There are several examples, and one of the important property here is every linear transformation can turns out to be a matrix. For example, you see this is earlier we have given this matrix, this linear transformation. This linear transformation can be written as 3, 5, minus 6, x1 coordinate minus 2, x2 coordinate minus 7, and x3 coordinate 1. So, every linear transformation can we write it as a matrix and vice versa. Every matrix can be written as a linear transformation. So what if we are interested in all these things? We want to study matrix analysis. So if we want to study matrix analysis, if we know what is linear transformations and what is matrices, then we can understand matrix analysis properly. That's what is the motivation till now. Now let us start matrices. Till now what we have discussed, every matrix can be represented as a linear transformation, as well as every linear transformation can be represented as a matrix. Now my theme of talk enters what we can see. So we know matrices, which are square matrices, rectangular matrices and all. And we can find what is its determinant and what is its submatrices. Submatrices, what is submatrices? For example, 2, 4, 5, 6, 7, 8 is a matrix. And we will remove this column. If we remove this column, I will end up with a 2 by 2 matrix. This is called a submatrix. Similarly, you remove this column, another submatrix. You remove this column, another submatrix. So we can generate so many submatrices, either removing one or more column or removing one or more rows. So there are several submatrices for given any matrix. And rows, these are called rows, and these are all called columns. And rank, what is rank? Rank is how many, see, every matrix, as I said, number of rows are there, number of columns are there. In that columns, how many non-linearly independent rows are there, or how many non-linearly dependent columns are there. So linearly independent columns are there. That linearly independent number, how many, that number is called rank of a matrix. And how to find? Taking elementary row operations. Make elementary row operation. I hope every one of you know what is row echelon forms. So the row echelon forms means taking last in last, taking some operations on row, scalar multiplications or additions, making last row as 0. For example, let me take 1, 2, 3, 4. 1, 2, 3, 6. What is a row operation? Multiply first row by 3 and subtract with the second row. If I multiply with this 3, 1 times 3 and minus 3, it will be 0. First row I am keeping as it is. Second row I am changing by multiplying first row by 3 and subtracting my second row. So if I multiply this row, this element by 3, it is 6. 6 minus 6, 0. So we are making complete row is 0. We have only one row. So therefore, it has only one linear independent row. Therefore, rank is one submatrix. So such kind of operations are called elementary row operations. So by taking elementary row operations, we can find what is its rank, as well as what are the linearly independent rows are there for that matrix. Now, what are eigenvalues? Eigenvalues, we know definition, but I'm trying to give a different view in the geometric view. What we have discussed that linear transformation T transforms vectors of this is my first space, R2 space, my plane, and this is another plane. My T is mapping, my T is a mission taking elements of R2 to again R2, this plane to this plane with some rule. What I am interested in, I am interested in vectors. Suppose this is my vector, such a way that if I transform T, if I apply, if this vector goes through this mission T, I should get another vector which is in the same direction. I want vectors which should not change its direction after applying the transformation T. Such kind of vectors we call it as eigenvectors. So let us see what we are interested in. We are interested in vectors V such a way that V and TV both are in same direction. That is equivalently saying that these are linearly independent. That's equivalently saying that one of them is completely dependent upon others. That means this lambda part, it is dependent upon others. Whatever it is spending and depend upon the others. That's equivalently saying that if I take it to this side, TV minus lambda I times V is 0. That's equivalently saying that this matrix V upon 0. That's equivalently saying that this determinant is 0. So this is what we are learning. A matrix, a lambda is said to be eigenvalue if this determinant is 0, and it's said to be eigenvector. This satisfies this property, and that's what is the classical definitions. But geometric wise, it is very smooth. What is the smoothness is eigenvectors are nothing but the vectors which does not alter direction after applying the transformation T. And how many eigenvalues or eigenvectors we may have? Because we have only two directions perpendicular. Therefore, it may have only two eigenvectors. That means two eigenvalues we can have for two by two matrices. And a norm of a matrix, I'm going to discuss. What is norm is, what is the distance? A matrix norm is nothing but, suppose if I take A, how much distance this A is from zero matrix. So there are similar way. For example, if I want to calculate distance from here to my hometown, there are several routes. Therefore, I will have different distances. And with this many ways, I can calculate distances. One of the important distance is 2 norm, which will be used for finding errors. And another important norm is Frobenius norm, which will be maximum eigenvalue of A. Now, coming back to our first topic, diagonalization. What does the meaning of diagonalization? What is the motivation? Motivation is two motivations we can discuss for diagonalization. One, coming from diagonal matrices. We know diagonal matrices. Diagonal matrices are very easy to handle. Why? We know what is its determinant. We know what is its how many linearly independent rows are there, or we know what is its rank, or we can find what is its inverse, or we can find its square. Isn't it? What is the inverse of this matrix, diagonal matrix? Just taking 1 over first place 1 over of this element, second place 1 over of this element, third diagonal element of 1 over of this element. So if we take such another diagonal matrix, 1 by A 1 1, 1 by A 1 2 2, like this, rest all zeros. This is inverse of this matrix. So finding inverses, handling matrices, handling diagonal matrices are easy. That's why question is that, given any matrix, at least given any square matrix, can we make it as somehow a diagonal matrix so that we can able to find its inverse or its square, its rank, its eigenvalues very easily? What are the eigenvalues of a diagonal matrix? The diagonal entries. So similarly, can we find, given any square matrix, its diagonal form such a way that our operations on A is simple? And what is second motivation? As we said, every matrix is a linear transformation from a space to other space. For example, take a 3 by 3 matrix. It is a linear transformation from our space, three-dimensional space, to three-dimensional space. Suppose if this three-dimensional space divide into two spaces, this plane and this line, such a way that my T is my matrix is invariant under these spaces. That means that on this plane, T maps elements on this plane to same plane, and on this line, T maps elements of this line to same line. That means I can treat it that as two linear transformations, T1 to T2, and T1 is on that plane to plane, and T2 is line to line. Since it is one-dimensional, studying this matrix, one-dimensional matrices or one-dimensional linear transformations are easy. Similarly, studying two-dimensional matrices are easy. So if I study these two, that's equivalently saying the studying of these three-dimensional matrix. That means that can we partition our R3 such a way that our matrix is invariant under that partitions? So if it is so, how we can do? So these three questions answers are coming from our diagonalization. So how it is coming? For diagonalization, we need symmetric matrices. We know what this does mean by symmetric matrix. Symmetric matrix are real entries matrices with T is equals to T transpose. And we have some properties of symmetric matrices. One is symmetric matrices, all eigenvalues are real numbers. Symmetric matrix will have exactly n eigenvalues for a n by n symmetric matrix. And eigenvectors corresponding to distant eigenvalues are orthogonal, that means perpendicular. The eigenspaces are invariant and orthogonal. So here we are getting invariant and orthogonal, which gives our diagonalization theorem. What is the diagonalization theorem? It is called spectral theorem for symmetric matrices. A symmetric matrix is symmetric if it has eigenvalues which are n, and it has an orthogonal basis consisting of eigenvectors. That means that the eigenvectors will form a orthonormal basis, which is very fantastic, very significant. This gives very significant role. Why it is so? Let us see. Suppose lambda 1, lambda 2, lambda n are eigenvectors, and v1 is eigenvector corresponding to lambda 1. Since we are in n dimensional, our vector should be n dimensional vector. That means it should have n components. And v2 is eigenvector for corresponding to lambda 2. Similarly, v3 is eigenvector corresponding to lambda 3. Similarly, vn is eigenvector corresponding to lambda n. If we have all such kind of things, we know that these are orthogonal. This gives that I can write my A as V transpose times D times V, where V is the corresponding eigenvectors. The first column of V is our V1. Second column of V is our V2. Third column is our third eigenvector V3. Nth column is eigenvector corresponding to N. And what is our D? D is a diagonal matrix with diagonal entries are eigenvalues. Exactly. So here we have to bit careful. The carefulness should be, if we are writing in D first eigenvalue lambda 1, this column should be corresponding eigenvector. We cannot write, for example, the eigenvector of lambda 2 cannot be put in first column. Eigenvector of lambda 3 cannot be put in nth column. We have to put very carefully. Then only this equation validates. So what is the use of this? If you look at our A, what is our A? Our A is symmetric matrix. We did not say what is its eigenvalues. Exactly, can we say it's a find its eigenvalues, or what is its rank, or what is it invertible? If it is so, what is its inverse? What is its square? We don't know. But from this, we can find all these things. For example, if this is given to us, eigenvalues are diagonal entries are D. Rank of A, how many non-zero eigenvalues are in diagonal entries? That is the rank of A. It is very trivial. And not only that, A is inverse of A. We can write it like this. Even though A is not invertible, that says that one of the entry will be 0. But take reciprocals of all other non-zero entries and find this multiplication, that gives generalized inverse of this. That means that even though A is not invertible, we are trying to find A inverse for that, which is called generalized inverse. Similarly, we can find squares very easily. A square is just take D square. What is D square? D is a diagonal matrix. Squares of D is only taking lambda 1 square, lambda 2 square, lambda 3 square and all. Rest V and there is no change in V. V is fixed. Similarly, A power n's also we can see. This is supposed to be n. A power any n we can calculate. A square root we can calculate. A kth root we can calculate. Of course, A power any fractional number also we can calculate. So our life will be very easy if we have spectral theorem for the matrix. But if you look at very carefully, If we get such kind of thing, only we should have symmetric matrices. Now questions are coming several things. So where it will be applicable, or can we do non-symmetric matrices? So that gives motivation to do SVD. What will happen to non-symmetric matrices? This gives, SVD gives not only non-symmetric matrices, it will give any non-square matrices. You take any rectangular matrix, we can get some diagonalization. How it will be? First of all, let us define symmetric matrix. Symmetric matrix is, sorry, let us define positive semi-definite matrix. Positive semi-definite matrix is a symmetric matrix with eigenvalues are non-negative. We have positive non-negative eigenvalues. And for example, if I take any square rectangular matrix, square or rectangle, A dagger A, that means A transpose, this is A transpose. A transpose A or A transpose, both are positive semi-definite matrices. The eigenvalue, these are positive semi-definite matrices. Therefore, eigenvalues are real as well as non-negative. Those eigenvalues are called singular values of A. And spectral theorem gives us that A can be written as U dagger times singular values times V. What is U dagger? U dagger is, U is a matrix of n by n size, which are coming from eigenvectors of A transpose A. We know that this S1, S2, S3, Sn are eigenvalues of A transpose A. That means singular values of A. For S1, there is an eigenvector for A transpose A. That is this vector. For S2, there is an eigenvector for A transpose A. That is this vector. Like that for Sn also, there is an eigenvector for A transpose A. That is this vector. That means that if I know eigenvalues or eigenvectors, calculating this and this are easy. And using eigenvectors of A transpose, we will get this one. So we end up now with, for given any square or rectangular matrix, we can have a diagonalization method. Again, what are the applications? Even for non-square matrix, we can find its inverse. For a non-square matrix, what is the generalized inverse? Generalized inverse is U dagger sigma inverse V. What is sigma inverse? Sigma is this diagonal matrix. Take its 1 over S1, 1 over S2, 1 over S3 and all. Whenever it is 0, make it 0. Whenever it is not 0, take its reciprocals. Then we can find what is generalized inverse of even non-square matrix, which is very useful in computer science, even in electrical engineering. We can find A square. What is A square? A square is just U transpose sigma square V. What is sigma square? The squares of these elements, which is finding easy. Similarly, we can find any nth root or any power, any fractional power of A. So there are several applications of this diagonalization, but these are all mathematical application. Now, can we do some applications which are non-mathematical, which has some good interesting thing? First application is low rank approximation. What is low rank approximation? Suppose A is very big matrix. Let us say A is 1000 by 1000 matrix. I have small computer. I cannot save my all 1000 by 1000 entries. I can save only 100 by 100 entries. So what I want? I want to find a 100 by 100 matrix such a way that A and AK as very near. Very near. So such kind of approximation is called low rank approximation. What does it mean that very near? Suppose A is a 1000 by 1000 matrix. I want AK such a way that the distance between A100 to AK should be less than distance between A1000 by any K which is of 100 size. Take any 100 by 100 matrix. This distance should be bigger than this distance. So such a AK We are interested in because it is very near to our A1000. Therefore, and I have a computer which I can save 100 by 100 matrices. Therefore, such a reduction is called dimension reduction or low rank approximation. So how we can look at? Look at the following. Suppose we have a 1000 by 1000 matrix or 1000 by 10,000 matrix, our A. And we have a decomposition. This is by 1000 by 1000. This is by 1000 by 1000 matrix. This is by 10,000 by 10,000 matrix. Suppose if my matrix is 1000 by 10,000 matrix, I have like this decomposition. But I want to say only matrix, some matrix of 100 by 100 size. What I will look at, this first 100 by 100 matrix I will pick, this submatrix, and this first 100 by 100 matrix I will pick, and first this 100 by 100 matrix I will pick. I will multiply this, and then I will get a 100 by 100 matrix. And I will make sure that this S1, S2, Sn are in decreasing order. That means S1 is bigger, S2 is second bigger. What is S1, S2, S3, Sk? These are singular values of this matrix A, and S1 is largest singular value, S2 is second largest singular value. Similarly, Sn and 100 is 100 largest singular value. If I take such as largest singular values, if I make it that 100 by 100 properly multiplication, I will get only 100 by 100 matrix, which is very near to A. Why? All other elements are lesser elements. So if I take any 100 by 100 matrix, rank may be more. That means distance may be more. So this is the way I can use my SVD to find low rank approximations. So this is the mathematical proof. As I said, I will remove this proof. I will ignore this proof for discussion. If somebody have any doubts, I will come back here after end. For example, let us see, this is very big matrix. We cannot handle, but I want to find 5 by 5 matrix which is near to A. How we can do? We can use a MATLAB or Python codes to find its SVD. Look at, this is the matrix. And this is first rank approximation of this matrix. This is second rank, this is third rank, this is fourth rank, this is fifth rank. For example, let us see. I will give one application to, let us discuss one application in electrical computer vision. In that, I need some background on images. What is images? Images are pixels. Pixels means I will have small dots. In each dot, some color code is assigned. So those are, for example, let us see this one. Here I will have, let us say, 1000 by 1000 pixel. That means here 1000 color, in 1000 by 1000 colors I have. Here also similarly, the color codes coming from this RGB. So similarly, these are the color codes. Each dot is one of the color code. That means that every color code I can give one number, that I can convert this image as a matrix by, let us say, if I have more resolution, that means we have more colors, we have more dots. That means that I have a very big size matrix. For example, let us see this matrix, this image. This is of around 5000 to 5000 by 5000 colors are there in this, that dots are there. And I want to, and the size of this one is very big. This means what is that size? How many colors, how many, what is the intensity of this image? I want to look at the intensity. I want to look at the intensity, and I want to size it, I want to reduce its size. How I can reduce? So if we look at this one, this has 500 rank approximately. That means that here 500 different colors codes are used in this image. If I take first 5 color codes, first 5 iterations, first fifth this, as I said, every image can be converted to a matrix. for this matrix, if I look at 5 by 5 matrix or 5th order approximation, and if I look at its corresponding image, that is this is the corresponding image of 5 by 5 size of the corresponding 5th rank approximation. It takes, the memory takes for this, saving this image takes 99% less than this original image. And this image is 10th rank approximation image. That means for this matrix, for this image, let us say for this image, the corresponding matrix A. If I look at A5, that means that the 5th rank approximation of this matrix A and the corresponding image, if I look at, that is the corresponding image, and that image will take only 19, it will take 99% less than space than the original image. And if I look at A10, I hope you can remember what is A10. A can be written as U sigma. In sigma, I have 500 non-zero entries and V. In this, only 10 non-zero entries you take and remove all other non-zero entries and make it to 0. And that will be our 10th rank approximation. For that 10th rank approximation, the image is this one. And this will take 95% less space than the original image. Look at A20. And the A20 corresponding image is this one. And it will take 89% less space than the original space. If I take A60, 60 rank approximation of the original image, that image is this one. And the corresponding image take 84% less space than the original image. If I take A100 and the corresponding image is this, and this will take half of the space than this. That's equivalently what we are doing. We are compressing our image. We are reducing size of our image using our SVD technique. SVD technique is pure mathematically based on technique one can use to compress these images. So what we are doing in our computer science or in our applications, compressing image, reducing image size, reducing the quality of the image, that's taking that, given any large size matrix, taking it to corresponding whatever. Suppose I can say only 100 by 100 matrices in my phone. If there is any sorry, if there is any photo, suppose if I download any photo from the internet, if that photo has resolution 500 by 500, what my phone takes, immediately my phone converts that 500 matrix into its 100th approximation matrix, and that 100 approximation corresponding image it will save in my phone. That's why the image quality is reducing and memory also reducing. So this is one of the very famous applications of SVD. And let us see another application which is called PCA, Principal Component Analysis. So this was started in 1901 by English mathematicians, and they used a different purpose. They used it for different purpose, and we will see from mathematics what we can do in this. What is this? What we want to see in this? Suppose these are the data points we want to study. These are the data points we want to study. What we can see here, data points are mostly in this direction. So if I study data points on this direction, that's fine. That says that if this data, in which direction the data spreads more, that direction is very important for me to study. If I study this direction, then I can look at, more or less I can study my data. So this direction is somehow called principal component or principal dimension. How we can get? Similarly, let us see the same data is mostly spread in this direction, and this direction spread is more, and this direction spread is little less. And for in this case, we say that this is principal axis and this is called second principal axis. How we can get this one? Let us go back to let us go back to our vector spaces. So these are the vectors in Rn we want to study. First of all, sorry. Let us look at given y vector. That means that this is somehow the distance between corresponding internal components of that, and look at its image. We say that all internal components are equidistanted. Then we will have spread in only one direction. Let us see. But what I want to say is, given any x, find its SVD. SVD is distances, corresponding distances, standard deviation, and variation. What we want, which direction we will have more spread. That means which direction we will have more variation. That is given by covariance matrix, which is defined. Covariance matrix is defined in this fashion. Covariance matrix is given any data. Covariance matrix is this one. Fortunately, this matrix can be written as this way: B into B transpose, and B is some matrix. We know that for given any matrix B, B times B transpose is positive semi-definite matrix. Therefore, we can have spectral theorem. By spectral theorem, we can find what is eigenvalues and what is eigenvectors. So those eigenvalues are eigenvectors. The first eigenvector, the eigenvector corresponding to maximum eigenvalue is called the first principal component. The the eigenvector corresponding to second maximum eigenvalue is called second principal eigenvector. So let us see one application. What is the application is okay. Finding eigen. This is same. Keep it. Yeah. This is what I am discussing. The principal eigenvector. The first eigenvector is nothing but this V1 is nothing but eigenvector corresponding to maximum eigenvalue of the covariance matrix. And ith principal eigenvectors, ith important vector for us, or ith direction which has more spread. Ith spread which has suppose V1 is the direction where more spread has happened. Like V2 is second more spread. Vi is ith more spread. Where we can get that vector is eigenvector corresponding to ith largest eigenvalue of the covariance matrix. So how much we can get? The percentage, what is the highest, the data, this much percentage of data I can study by studying first eigenvalue, first ith eigenvectors. First, for example, if I study only in the V1 direction, lambda 1 by summation of all lambda i's, that much percentage of information I can get. If I study with respect to V2 direction, lambda 2 by the summation of percentage I can get information of the original data. For example, this is also used for dimension reduction. For example, if I want to study only, suppose my data is given in 100 dimensions. If I want to study 5 directions, which directions I need to study is the first principal 5 directions. If I want to study first 10 directions, I need to study only first principal 10 directions. How we can get that are nothing but first 10 eigenvectors Those are corresponding to first biggest 10 values of the covariance matrix. That's what the details are given here. And another application was studied by Professor Adam. What he wants is he has taken 100 birds for which he calculated length of each bird, wingspan of each bird, and weight of each bird. What he want to decide is to fly a bird. Length of the bird is important, or wingspan is important, or weight is important. So we know practically wingspan is important. So how it can be decided is the following. Mathematically, how we can prove is like this. So on his data, this is the covariance matrix. And for this covariance matrix, this is lambda 1, lambda 2, lambda 3. That means lambda 1 is highest. So we need to pick this direction. What is the eigenvector corresponding to lambda 1? So V1 is the eigenvector. Corresponding to V1 is the eigenvector. It says that length, we can see that this corresponding to wingspan, because the first variance is about wingspan. Therefore this corresponding to wingspan, and wingspan will have more effect than birds, and that effect is 92% of effect will be there. Yeah, that's it. I will stop here, and I will open for questions. Sorry, due to time lag, I was little fast. Yeah, thank you very much for listening. If anyone have any questions, I am happy to address.
Dear participants, can anyone please raise your queries related to this? Sir, as you said that when we download an image from internet,
Yes.
you said the size and the dimensions will be reduced to 100 out of 100 for the mobile.
Yes.
But what about the desktop version, sir?
Desktop version depend upon the like capacity, how much storage you have.
In case if you have enough storage,
Yeah, if we have enough storage, we can it will download accordingly.
okay, the same size will be replicated,
Yes,
right?
replicated.
So there is no change.
No change, unless if you put any condition on your downloading factors.
Okay. Now there is a problem. I think when we check in the case of WhatsApp while we are
Yeah, we don't download because see our mobiles are does not support that much saving capacity.
okay.
So see, our mobile, maybe we are having a capacity of around 200 GB.
No.
In that 200 GB, each download will have 3-4 MBs.
Okay.
3-4 MBs means it will support only 100 by 100 images. 100 by 100 size images. So if you have more resolution means the matrix corresponding to the image is bigger.
Okay.
So it will download, it will reflect, it will look at immediately, it will convert, look at its SVD, it will convert what is your capacity of your mobile, and it will take corresponding eigenvectors, and it will convert it to corresponding dimension, and it will save corresponding image.
Okay.
For example, in when we are, suppose see, if we are applying any positions, they
Yes,
will
sir.
say that we need to upload either our photograph or any document of 1 GB, 1 MB or 5 MB, 10 MB,
Mhm.
where we have more capacity.
Okay.
So there we need to compress our file.
Yes, sir.
What does that mean to compress that file? Compressing means it does not size. For example, if we have size of our photo sizes of 10 by 10, it won't reduce 10 by more than 10 by 10 size. The pixel images, image intensities,
Yes, sir.
the image intensities will decrease.
Okay.
The sharp, for example, in pixel, suppose you have, let us say, your phone is by 1000 by 1000 pixel.
Yes,
What
sir.
does it means? That your foot, all images of your phone is by 1000 by 1000 matrices only.
Okay.
So if there is any photo, if you downloaded a photo or if you taken a photo from web studio, they will
Hello.
have big cameras.
Okay.
They have lot good resolution. That means they have more pixels. By 10 by 10 size itself, very they will have like each pixel of 0.1 mm by 0.1 mm. So they will have big size matrix. So that size matrices, it will, we have to convert into small size matrices.
Okay, sir.
The compression is only, of course, this SVD technique is long old method. So they have some refined techniques using this SVD only. So using this, at the end of the day, compression a file means reducing its size, reducing the matrix of the corresponding photo. For example, you see, if you take a photo from a photo studio, if you
Yes, sir.
zoom it, still your photo clarity will be fine, because for that photo, each 1 centimeter by 1 centimeter size small portion will have lot of different color codes.
Yes, sir.
Each color code gives one number. That means you will have lot more numbers. Size of the matrix is very big. But for phones, for 1 cm of image, we will have maximum 2 by 2, 2 color codes or 3 color codes or 4 color codes.
Yes, sir.
That means we will have only 2 by 2 color codes. So if I drag too many things on my mobile, after that it will get like a squares. One square is of one image, one color, another square is in different color, like that. That means that two, three boxes of original image is merging to corresponding one box, one color. As I said, you think if you taking a photo from photo studio, what I'm saying is every point denotes only one color. Different points denotes different color. But if I convert that, if I take that photo in my mobile, what my mobiles take, let us say 4 points. It will combine 4 points, and for those 4 points, my phone will allot only one color. That means instead of 4 by 4 matrix in original photograph, in my camera, in my mobile, I will have only 1 by 1 matrix. 4
Yes,
by
sir.
4 means 4 different colors. 1 by 1 means only one color. I hope you are understanding what I want to
Understood,
say.
sir. Just one more question. I'm
Yes.
just new to this mathematics. We knew that basic concepts, but I don't know about this. Why can't we use a, symmetric matrix? I mean, what we call the sparse matrix to retain the original codes from the
See,
original page. Is
that
it possible to retain the same thing?
see sparse matrices. What sparse matrices? Sparse matrices makes most of the non-zero terms zero. But what LCA or PCA does, for example, see, you have color codes numbers, let us say 0.9, 0.8, 0.5. What sparse matrices do, all 0.9 onwards, it makes to 0.
Yes, sir.
But what SVD does, 0.4, it won't go to 0, it will go to 0.5.
Okay, sir.
So you don't have that much difference. That means that you don't have that much variance for the photo if you use SVD rather than sparse matrix. You can do, there is no issue, but you will have a lot of loss of information will be more. That's what I want to say. You will have more loss than this method.
Thank you, sir, for clarifying all your doubts, and your session is very informative, and we shared a lot of knowledge to all your participants, sir. We really enjoyed your session. In fact, which is some concepts we really learned from your talk. We do expect a lot of talks in future also, and from our all the participants, and we'd like to say thank you once again to all, and I request all the participants, please turn on your videos so that we can have a photo with experts. Yeah, thank you, sir. Thank all the participants. We'll catch you in the next keynote on at 1 o'clock. Sir, just also, sir, we are very thankful for you being as a keynote speaker for this second international conference.
Yeah.
And any other participant, can you please give your feedback about the session?
Yeah, yeah, okay. Thank you very much.
Thank you very much, sir.
Thank you. Thanks.
All the participants, please fill the feedback form, and we also register your attendance. That is also we are considering, and we request you please be active in the group during the session to ask any queries, and to, because we are inviting the experts, right? This is the right time to grab some knowledge from the expertise, and we do expect on the next session by 1 p.m. Thank you.